All right, so let's go through the steps, and let me give you the scenario, and then we'll go through a couple of examples. So this is section 15.4, and what we're going to be doing here is we're going to be testing claims about two population, in this case, not means. We had two sections in chapter 11 where we looked at claims about two population means. In this section, the claims are going to be made about medians. And again, dependent samples. So if you're going to compare this test to one that we've done before, compare it to the test that we did in section 11.2. And if you recall, we had one set of numerical data values here that we put in L1, and there was another set of data in L2, and we call these matched pairs. Somehow they're linked. It could be a pre and post test. It could be, weight before and weight after, and in the middle there's an exercise program or a diet program. But we're going to have the number of cases here, 1, 2, 3, 4, down to our sample size, n, and then we put the numerical data, the pre-values in L1, the post-values in L2, and then in L3 we calculate the differences. You can do L2 minus L1 or L1 minus L2. So you're going to be doing the same thing, but you're going to be building a much bigger table than what you see here. Most of the time our data sets will be fairly low for this test. And generally what we have is one population, and we take one sample, but we're taking two different readings from that one sample. So it could be a pre and a post test score, or something about before and after. Somehow these data values are matched, linked together. Knowledge of one would give you information about the other. Okay, let's take a look then at the steps. Step 1 is the hypotheses. And in this one, if you remember, back in section 11.2, we had the mean of the differences was equal to 0, and that's what our null hypothesis would be. This test is very, very similar to that, except instead of means, the claims will be made about medians. So the median is equal to 0. The null hypothesis is always a statement of no difference, and we're going to be subtracting. And if there's no difference between these two values here, say one is 15 and the other one is 15, then when we subtract them, we're going to get 0. If you got a bunch of numbers over here closer to 0, some maybe -1, some +1, but all very close to 0, then the average of all these numbers here, or the median of all these numbers here, should be close to 0. So if there's no difference between the two variables, the mean of the differences will be 0. Although this is median of the differences. All right, and then the alternative hypothesis, you're going to use one of these three signs, but you're still going to have 0. And it depends on the claim. Has there been an improvement from before and after? Has there been a decline? In case of weight, might be interested in a decline between before and after. Or is there no difference at all? So as normal, when you define this, you want to say the median of the differences. And then you need to indicate, what you're subtracting. All right, there's no difference on step 2, the level of significance. That's the alpha. We're still going to have an alpha. This is, we always have to specify an alpha in these tests. That's the probability of making a type 1 error. And we want the probability of making an error to be low. So we choose these low numbers here. All right, so the 3 is where all these tests diverge, right? And they're all slightly different. And the test that this Wilcoxon discovered, the Wilcoxon match pairs signed ranks test, is you have 2 sets of data and you subtract them to get the differences. So then we have the median of the differences. So we're going to have an X variable and a Y variable. Our table is going to be expanded. So the first thing we're going to calculate is D, the difference. So we're going to take X and minus and subtract the Y value. So whatever's here and whatever's here, subtract them, and that goes here. Now, some of these differences will be positive, and some of these differences will be negative. So the next column, what we're going to do is we're going to convert them all to positive numbers. And that's what the absolute value does. This is a mathematical function. This is the absolute value of all the numbers in here. So to get the numbers in this column, all you do is just bring over these numbers in this column, just bring them over exactly as they are. But anything that's negative, just turn to a positive absolute value. All right, then what we're going to do is we're going to rank those values of the absolute value of D. And we're going to start with the smallest one. And we're going to give it a ranking of 1. And then the next largest difference, we're going to give a ranking of 2. And then the next largest difference, we'll give a ranking of 3. Now they're all going to be positive, so we're going to just be ranking a bunch of positive numbers. We'll start with the one closest to 0, and then move up from there. If there's a tie, we'll split the rankings. I'll show you how to do that. And then finally, you're going to have here the signed rankings. So what we're going to do here is we're just going to take all of these rankings here and bring them on over. But if the difference here was negative, then we're going to switch the sign over here to a negative. If the difference was positive, we're going to leave this one here as a positive. So we're actually going to assign signs, plus or minuses, to the ranks, 1, 2, 3, 4, 5. If there's 12 data values, you're going to have the ranks 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 here, unless some differences match, as you'll see. So you're going to have some positives here and some negatives going down. Then you're going to add, and again, what we do in step 3 is to calculate the test statistic. So what you do is you create this entire table, and then you use this table to calculate the test statistic. And the test statistic is going to be, T is our test statistic. And T will take on a number that, just like our previous test, what we choose for T depends on whether we're dealing with a one-tailed left, a one-tailed right, or a two-tailed test. So what is this one? Well, if you have a alternative hypothesis in which the median of the differences is greater than 0, we know this as a right-tailed test, then the test statistic in this case is going to equal the absolute value of T minus. All right. Now, over here, T minus equals the sum of all negative rankings. And we're going to calculate its counterpart, T plus, equals the sum of all the positive rankings. So this is the first scenario. Since we have a right-tailed test, a left-tailed test, and a two-tailed test, we're going to go and define what the test statistic is for each of those 3 tests. If in your alternative hypothesis, you have the mean of the differences is less than 0, okay, so this is a left-tailed test, then T is going to be equal to T plus. Now, I put absolute values around t negative because it's going to be a negative number. And we want our test statistic to be positive because, again, we're going to compare it to a critical value, which is always positive. And we wouldn't want to select the test value that's always negative and compare it to a critical value that's always positive, because the test statistic will always be negative or always be less than the positive critical value. All right, so that's a plus. All right, so I'm running out of room down here, so I'm just going to write the other one here. The third scenario is if the alternative hypothesis uses the not equal to. We call this a two-tailed test, same as before. Then t is equal to the smaller of t plus or t minus, again in absolute value. So the test kind of runs similar to the one sample sign test, where if you have a one-tailed left, you use number of pluses, one-tailed right, you use number of minuses, or vice versa, and then the two-tailed test, you use a minimum. All right, so that's the test statistic, and there is no p-value approach to this one, and so there's one way to determine whether you reject the null hypothesis, and it uses the critical value. So here it is. If the test statistic, and we know that to be t, we just identified what that number would be, is less than the critical value, then we reject the null hypothesis. On the other hand, if the test statistic, and t, is greater than or equal to the critical value, then do not reject the null hypothesis. Now, there's no p-value that we would collect, that we can calculate here. And so this is really the only test that we use to determine whether we reject or not the null hypothesis. So there's the decision. And this really would be step 4, decision. And here's the decision rule. What's common between these two tests, and well, one of the things that's common, we talked about one thing already, is that you compare the critical value or the test statistic to the critical value, and you reject if the test statistic is less than the critical value. Always less, never greater. Now, the critical value is going to be, this t of alpha, or if it's a two-tailed test, t of alpha over 2. So if you see this notation of t of alpha or t of alpha over 2, they're really talking about the critical value that you get from table 12. And then the 5th step is the conclusion, and there's really no difference in how we would report this out. You'd report this out in the same way that you would report out in section 11.2. There's evidence to reject the claim. There's not enough evidence to reject the claim. There's evidence to support the claim. There's not enough evidence to support the claim. 4 different scenarios. Okay, let's now go into an example so you can see how this is applied and some of the subtleties that you'll see in the ranks. We're going to, for all of these problems, we're going to construct this table, because it's this table that helps us identify the test statistic. All right, so here's the name of the test. You have these notes in e-learning, and I just covered these. We're going to be using the small sample case just with n less than 30. This one has a large sample case as well, but we can just, it's here if you want to use it, if you find a project or something in which you have to use it, but we're not going to be using the large sample case. So you can ignore that information as well. So focus in only on the small sample case where we have less than or equal to 30. And then the table we use is table 12. And notice you have critical values all the way up to 30. So we're going to be using only the small sample case where we use this table. Here's where it talks about the critical values. For a two-tailed test, it's T of alpha over 2. And for a one-tailed test left or right, it's T of alpha. But that's the critical value. Up here, it tells you if you're dealing with a two-tailed test, that you're going to take the smaller of T plus or absolute value T minus. Here with the less than sign, T plus. And here with the greater than, T minus, absolute value. We want our test statistic to be a positive number. And the only other thing I want to show you here is the decision rule down here. I wrote it like this because I think this is maybe easier to understand. And they wrote it like this. And notice in every single time you reject if T is less than the critical value. If the test statistic is less than the critical value, you reject. Otherwise, do not reject. All right, I want to take you to a table where we are going to a table similar to the ones that we're going to create. So you have the number of cases here, 14, and it turns out that the n that you come up with might not equal the number of data values you have or differences that you have. We're going to ignore all those zero differences like we did in the previous test. Now here you see your X list. Maybe we'll put those in L1, and your Y list. Maybe we'll put those in Y2. And then here you calculate the differences. And it looks like they're subtracting X minus Y. So they're taking this number and subtracting this number to get that number. This minus this to get this. When you take a smaller number and subtract a larger number, you're going to get a negative. So they subtracted L3 minus, or L3 by subtracting L1 minus L2. All right, I'm going to add one more column here just so you can see the intermediate step. Okay, so these are the differences. Notice that some of them are positive and some of them are negative. Then the next column is the absolute value of the previous column. And so if you take over all these numbers and just bring them over and just convert every single one of them to a positive number, that's what absolute value does. So a positive 0.4 comes over as the same thing, positive 0.4. A negative 1.3 comes over as the positive version of that. Same thing with all of these. All right. I'm going to add one more column, and I'm going to call it the rank of the D's. Actually, the rank of the absolute values of D's. And I want to show you what happens if you have a difference that matches. I mean, we want to rank them from the smallest one to the largest one, but what if you have two data differences that match? How are you going to take the rank, identify the ranks in that case? All right, now, because these are the absolute values, they'll all be positive. So when we rank them, we're going to rank them from the smallest one up to the largest one. Potentially, we're going to have 15 ranks. All right, so let's go through these numbers and identify the smallest number. 0.3, 0.4, 0.8, 0.7, 0.4. It looks like 0.3, that one, is the smallest one. So we're going to give that the rank of 1. Then we go up to the next largest difference. And the next one is 0.4. But 0.4 appears here, and it appears down here. So there's two versions of 0.4. Now the rankings that come next are 2 and 3 because we've already assigned the ranking of 1. So instead of giving one of these 0.4s a 2 and the other one a 3, what we're going to do is take those two rankings, 2 and 3, and we're going to divide by 2. Well, that's 5 over 2, which is 2.5. So instead of giving one a 2 and the other one a 3, we're going to split the difference and give them both 2.5. We want to give them the same rankings because later on we're going to add these rankings to determine the test statistic. But they're equal, so we don't want to rank one higher than the other. So for this one, we're going to give a 2.5, and for this one down here, we're going to give a 2.5. And then we continue. All right, so we've ranked 1, 2, and 3, so now we're on ranking 4, and the next largest number is, oops, looks like we have a 0.7 and a 0.7. So the next two data values to rank are in position 4 and 5. So what we're going to do is we're going to just assign them both the number right between 4 and 5, 4.5. So 0.7 here gets 4.5 and 0.7 down here gets 4.5. Now, there will be scenarios where if you have 3 different values that match, then what you would do is add all 3 together and divide by 3. It's like taking the average and then give each one of those data values the ranking of that average. Okay, so we've ranked 1, 2, 3, 4, and 5. So 6 comes next. And here we have a 0.8. There's no other 0.8, so this is going to get a ranking of 6. And then just kind of going through again. Next one is at 1.3. There's two 1.3s. Yeah, so 1.3 would come next. And the last ranking we gave was 6. So these two 1.3s will receive the ranking 7 and 8. But again, we're going to split the difference, and we're going to give them each a rank of 7.5. And that'll take us through ranking 8 on our way to rank up to 14. So after 1.3, any more 1 points? No. So here's a 2.1, anything less than that? No. So 2.1 would get the ranking of 9. We've already assigned up through 8. And after 2.1, 2.8 is the next one, so it gets the ranking of 10. And after 2.8, if you look at the ones that are left, 3.2 would be next, so it gets the ranking of 11. And then we have 5.1, 6.6, and 20.1. Here's the outlier, 20.1. So definitely the underlying distribution is skewed in some way. And since it's skewed, has an outlier there that could really throw off the result. So that's why using the median here is a better statistic to use than the mean. All right, so we have 12 and 13 and 14. And so we have the rankings of 1 through 14. And there's a formula that says if you take n times n plus 1 over 2, you should find that the sum of the rankings equal this. And so if you take 14 times 15 and divide by 2, what would that be? 105. So when you add up all these rankings, you should get 105. And that's a good check because the T plus and the T minus, when you add them together, you should get 105, and that's a good way to check. Okay, they didn't do this column. They went right to this column. Notice these numbers here match these exactly, except for minus, the minus sign. But all the rankings are the same. Notice that some of these are positive and some of them are negative. Where do they get the negative sign? They get it from the difference. So every time you see a positive difference, you're going to get a positive signed rank. And every time you see a negative difference, you're going to get a negative signed rank. So just bring over the ranks and then look at the sign of the D. Wherever you see a negative, attach a negative here. Negative, 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 negative. Everything else would be positive. All right, the next step when you see this is to calculate T plus and T minus. And one of those numbers will be your test statistic. And it really depends upon what the alternative hypothesis says, if it's a greater than, or if it's a less than, or not equal to. So what we're going to do is we're going to add all these positive ranks. So every time I see a positive, I'm going to put it up here and add those numbers together. We're going to add the positive ranks, we're going to add the negative ranks, and then we're going to compare. All right, so when you add up all these T positive numbers, you get 69. And then we're going to do the same with the negative rankings. All right, so if I can get it on here. The first negative ranking is negative 7.5, then negative 9, negative 11, negative 6, negative 2.5. And when you add up all those negatives, you get negative 36. It's usually going to be the case that the test statistic is going to be equal to the smaller of those two numbers, but not always. It really has to do with what kind of a tailed test you have, if it's one-tailed left, one-tailed right. So the test statistic depends on the alternative hypothesis, and it will be equal to either T plus or T minus, except for the T minus, we're going to put absolute values around it. So T plus is equal to 69, and T minus absolute value is equal to 36. Now, notice if you add those two together, you get the 105, which was this number up here. And that's to check to make sure that you have all of the correct rankings, that they add up to what they should add up to. It's a good check. So here's yet another test to, this step here is the step that you're always going to do, but a lot of times you have to start with just those two columns. So let's go to an example where we do the entire test from start to finish. Okay, so the first thing we're going to do is, and what they did here is we want to know if water is becoming clearer. So there was this lake at a community college near Detroit, near Chicago, Joliet Junior College Lake. And apparently they were treating the water because they wanted to clear it up a little bit. And so the way that they determined if their treatment improved the situation, or maybe it was just the environment that improved the situation, they took this, this disc. It's an 8-inch in diameter weighted disc, painted black and white so you could see it, the contrast, black and white. So just imagine it's like a, a discus, and they can somehow drop it. A rope attached to it here. It's a disc. It weighs, it's got a diameter of 8 inches. And they just lower it into the water. And they watch it. And you may have seen some bodies of water, like pools, for example. They keep a lot of chlorine in there. You can see all the way down to the bottom. And in some lakes are very clear as well, where, the lakes are 30 feet deep and you can see all the way down to the bottom, very clear. This lake here, not so clear. So what they did is the initial depth was on, and they did this for several different places inside the lake. And they took 8 observations on two different times. This one was, say, 2015, and they measured how far, and I believe this was in inches, so this is about 1 foot. So you can see how murky this raw water was. They dropped it about, what's this, 3 feet, 1 yard, about 1 yard, okay, length of my arm, into the water, and they could see it at 38 inches. But that's it. They couldn't see it once it dipped below 38 inches. And they took this measurement on May 11th, 2015. Then let's say 5 years later, after some treatment, or after they tried to improve the environment or something else, they did the same thing. They lowered this disc into the water and they observed it. Still see it, still see it, still see it. Oh, don't see it now. And then they brought it up and they measured the rope to find out how far the disc actually went down, where we could observe it. So that's their study. And you can see that, all right, we need to add a couple of columns here. And the first one we're going to add is D. And D is equal to the X minus Y. You're going to extend all of these tables. Now, in this first one, generally, we're just going to take this is the X and this is the Y. These are our two readings. And this one, we're going to take 38 minus 52, and that's going to be negative 14. So there was a difference in 14 inches. And because they could see the disc at a greater depth than they did 5 years ago, it appears in this case that the lake is getting clearer wherever they measured it at this point, because they can see the disc for a larger number of inches as it goes into the water. So what's important to note, because of the way we subtracted here, a negative number means that the lake is becoming clearer. If you go down to this one here, these were different areas of the lake. If you take 74 minus 72, then you're going to get a positive number 2. 5 years ago, they could see this disc 74 inches down. Well, in a current year, they could only see it for 72. So it appeared in that region, the lake was getting cloudier or murkier, or more polluted, or whatever you want to say. But positive numbers means that there has not been an improvement in the water clarity. All right, so let's fill in the rest of these. $58 minus 60, there's another negative, getting clearer. Here, negative 7, clearer. 2 here. This one's what, negative 12. 56 minus 58, negative 2. These numbers are whole numbers, so they're not so bad. If you get messy numbers, then you might want to dump them into your calculator and calculate the differences in that way. And this one here is negative 8. All right, now we're going to repeat what we did on this one here. Notice the columns we have. We need the absolute value of D. Then we want to rank them. Then we want to attach signs to the ranks. So the absolute value of D is not a major step, but you're just going to take all these same numbers, but you're going to take the positive of those numbers, right? And 2 final columns. After this one, the toughest part about this whole process is to rank these positive numbers. We're going to start with the lowest one. Okay, now the lowest difference is 2. And it appears 4 times. So what we're going to do is we're going to take the rankings 1, 2, 3, and 4. That's going to contribute 10 points to our either T plus or T minus. And then we're going to divide by 4 because there's 4 data values that have that lowest ranking. So this would be 10 over 4, which is 2.5. So instead of giving one of these 2s a 1, one of them a 2, one of them a 3, one of them a 4, when you add up those rankings, you get 10. So we're going to divide those 10 points, 10 ranking points, evenly. So each one of these 2s get a 2.5. So instead of seeing 1, 2, 3, 4, you're going to see 2.5, 2.5, 2.5, 2.5. That takes care of the first 4 rankings. The next number will be the 5th ranking. So after 2 comes, it's like 7. So 7 is going to take the ranking 5. And then 8's going to take the ranking 6. And then 12 is going to take the ranking 7. and then 14 is going to take the ranking 8. So our rule of n times n plus 1 over 2 still applies here. In this case, n is equal to 8. So the point total is going to equal 8 times 9 over 2, which is 36. So if you add t plus and t minus together, you should get 36 in this case. All right, the last thing we're going to do is to assign ranks. So I'm just going to bring over these same numbers and then go inspect the difference. Every time we have a negative on the difference, we're going to throw a negative onto the rank. Negative, 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 negative. That's a positive, so it stays positive. That one's positive. This one's negative. This one's negative, and this one's negative. So most of our differences are negative, and negative differences mean that the lake is getting clearer. Okay, T positive, I'm going to add the positive ranks. 2.5, 2.5. That one's easy. And T minus, I'm going to add all the negatives. I already know what it's going to add up to because I know the sum of those two is going to add up to 36. But let's do it anyway. Negative 8, negative 2.5, negative 5, negative 7, negative 2.5, and negative 6. And when you add those together, you get negative 31. I mean, the way I remember it is if your null hypothesis is less than, then you're going to choose the plus signs. If the alternative hypothesis is greater than, then you're going to choose the negative. So it's kind of you're choosing the opposite, but you may have to consult this a couple of times. So before we can decide which one we're going to choose, we need to write the hypotheses. So let's go back and write the hypotheses. Do you believe that the clarity of the lake is improving? It's getting clearer. It's getting clearer. You can see that disk as it goes deeper into the water. So the null hypothesis is that the median of the differences is equal to 0. By the way, in this section, the null hypothesis is always this. The only way it differs is in this sign here in the middle. And so to determine the sign, I just go back to one of these. If 5 years ago you could see only 38 inches, this Secchi disk, and in a current year you could see it deeper, that means you can see it deeper, so therefore the water is becoming clearer. And because of the way I subtracted, a negative number means clearer. So if we want to write the alternative hypothesis as our claim, negative numbers are what implies clearer in our case. So that's why I use the less than sign here. And if you use the less sign, because of this only, you know that the test statistic is equal to T positive. So whether you choose T positive or the absolute value of T negative depends solely on what that sign is. So you've got to get that sign right. And notice that T positive is a smaller number, and that's usually going to be the case than T negative. So T equals T positive, which is 5. Okay, now I'd like you to go to table 12 and find the critical value. What you need is you need to know that n is equal to 8, and you need to know that alpha is equal to 0.05. And that's it, the critical value. The symbol that we give to the critical value, since this is a one-tailed test, is T of alpha. All right, let me get this table out in case you don't have one. N is 8, alpha is 0.05. Write the value of the critical value in the chat. Here it is. Okay, good. 8, alpha is 0.05, there it is, right there. Notice that all these critical values are whole numbers. So it's unlike what we've done in the past. All right, 5. So here is for the small sample case, the decision. We've got the critical value and we've got the test statistic. So this says if the, and it's a less than test. So if the test statistic is less than the critical value, notice that that's strictly less than. It's not less than or equal to, it's less than. Reject. So you only reject if it's less than. So when you compare the test statistic to the critical value, the test statistic is 5, the critical value is 5, and those are equal, not less than. I think I wrote it out maybe here. This might be another way to think of it. If the test statistic is less than the critical value, then reject the null hypothesis. If the test statistic is either greater than or equal to, and in this case it's equal to, then we're not going to reject the null hypothesis. So our decision here, do not reject the null hypothesis. All right, and then the conclusion. I guess one thing I didn't do that we should have done is to calculate the median. All right, so what's the sample median of the differences? Here they are. There's only 8 of them. We can list them. All right, we have to list the negatives first. Negative 14, negative 12, negative 8, negative 7, negative 2, negative 2, and then 2, 2, 1, 2, 3, 4, 5, 6, 7, 8. So again, we're looking at the differences here, which contain both positives and negatives. There are 8 values, 4 on the left, 4 on the right. And so the number right between would be negative 4.5. So the sample median of the differences is negative 4.5. We see it's a negative number. We know that negative numbers mean that the water is getting clear. So we found this number, and then we do this test to see if that number is statistically significant. So it looks like on average, we can see the disc about 4.5 inches deeper. But as you can see from our test, that this difference that we observe is not statistically significant to enable us to reject the null hypothesis in favor of the claim. So even though we did see that the disc goes lower, it appears to be clear in many places, this difference is not statistically significant. So we're not going to have evidence to support the claim that the lake water is becoming clearer. So that's what we're going to write up. So say something like this. There's not enough evidence to support the claim that the lake water at Joliet Junior College is getting clearer. The clarity is improving. So we'll say it in layman's terms. All right, I now want to do a new example, and in the new example, what's going to happen is that some of these differences will be 0. That is, the before and after measure will be exactly the same. So when we subtract 2 numbers that are the same, we're going to get a 0 difference. How do we handle that? How does it come into our rankings? So there's a problem 16. This problem deals with the effect of aspirin on blood clotting. So they talk about blood clotting here. And there's a protein, thrombin, initiates blood clotting by working with another protein, prothrombin. It is common to measure an individual's blood clotting as prothrombin time. How long does it take after aspirin has been consumed in order for the blood to unclot? Or clot, however they're considering this. So aspirin is supposed to thin out the blood, which would lead to fewer clotting issues. And so if the aspirin is working, then the time that it takes would be a little bit less, I would think. Clotting stops the clotting, so the time that it takes to clot will be a little bit longer. Researchers wanted to study the effect of aspirin, so they randomly selected 12 subjects. and measured the time in seconds without taking aspirin, and 3 hours after taking 2 aspirin, now that the aspirin's in the body, they looked at the clotting time as well there. Okay, so does the evidence suggest that the aspirin affects the median time it takes for a clot to form? All right, so that's the problem. And so I'm going to create a new table down here so I can add to it. Here's a table that they gave in 2 columns, 1, 2, 3, 4, 5, 6, and then 7, 8, 9, 10, 11, 12. So the question is n going to be 12 in this? It's important to be able to identify n. It starts off at 12, but it might not end up as 12. So I'm going to write each of the 12 values in a table, x and y, and then we're going to have the d, which is x minus y. Then we're going to have the absolute value of the d. Then we're going to have the rankings of those absolute value of d's, and then we're going to have the signed ranks. All right, so I'm going to bring these numbers down, 12.3, 12.0, and so on. It looks like the clotting time, regardless of the individual, is all about the same. So everybody has a similar clotting time. These are seconds, so it's not a whole lot of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 2 more, 11, and 11.3. All right, so those are all the numbers in the first column. This is kind of the before. And then we have the after, and they measure it. So 12.0, 12.3, and so on. All right, so I'm just going to go down to this table now and complete the rankings. So if, you know, these are relatively close numbers, and so the differences will be pretty easy to calculate. But if you want, you can dump the x's into L1 and the y's into L2 and then subtract L1 minus L2. All right, so this number minus this one, it's 0.3. And this one, this minus this is negative 0.3. Negative 0.5. This one is 1.0, 13 minus 12. All right, so here's where you're going to see your first 0. There, 13 minus 13. Here's another one, 12.5 minus 12.5. This one is 1.0, 0.5, 0. This one is negative 0.5. Another 0, and negative 0.2. All right, here's what we're going to do with those zeros. Every time we have a 0, then of course the absolute value will be 0, and 0 would be the lowest one. Right here, there's no difference. So what we're going to do with this test is we're just going to ignore all of these zeros. And we're going to bring over only the non-zeros. But because we're reducing the zeros, we're reducing the number of our n. So now we started with 12, and we got rid of 1, 2, 3, 4 zeros. So now our n is going to be 8, and alpha is 0.05. And it's this n that you're going to use to determine the critical value, and not the original one where we had 12 values. All right, so from here on out, we're going to be using an n equal to 8. All right, these numbers here, I'm just going to bring them over, but they're going to be the positive versions. So they would look like this. Now there's no zeros. So we don't have to give the rankings 1, 2, 3, 4 to a bunch of zeros. All right, now the rankings. So all of these absolute values will be positive. So you start with the smallest positive number, and that gets the ranking of 1. All right, so when you look at these, the smallest number is 0.2. So that gets the ranking of 1. Then we have rankings 2 and 3. We've already ranked 1. We'll go to these 0.3s. These are the next largest numbers. So we have to take the 2 and the 3, split them, So we get 2.5 and 2.5. Notice those two rankings add up to 5, just like the rankings 2 plus 3 would add up to 5. All right, now here's a new one as well, because we want to assign, we're at 1, 2, 3, we want to assign the ranking coming next would be 4. But we have 0.5 appears 3 times. So there are 3 rankings that we want to assign to the 0.5. We don't want to assign them 4, 5, 6, but we want to take 4 and 5 and 6 and split those rankings among the 3 0.5s. This is 15 over 3, which is 5. So what we're going to do, instead of giving the rankings 4, 5, 6, we're going to give each of these 0.5s a ranking of 5. So now we're up through ranking of 6. Our n is only 8, so we've got to rank 7, and then we have to rank 8. Well, turns out that 7 and 8 also are the same number, so we're going to split the difference on the 7 and 8 and award each of them a 7.5 ranking. So there you see the 8 ranks. We're going to bring these numbers over, bring these rankings over, and the difference between the previous column and this column is that this one is going to attach a negative sign to some of those data values. If the difference is negative, then the rank will become negative. So negative, negative, these two here are negative, and then these two down here are going to be negative as well. We have, just like in our previous example, if you take 8 times 9 and divide by 2, the rankings have to sum up to 36. So your T plus and your T minus in absolute value should add up to 36. So T plus is equal to 2.5. We're going to add all the positive numbers, plus 7.5, plus another 7.5, plus 5, okay? And that adds up to 15, 20, 22.5. And T minus, add the negatives, 10, 11, 12, 13.5. So negative 13.5. And if you convert this to a positive and add it with this, these two numbers add up to 36. So you can be sure at this point that you've added the rankings correctly. All right, now to determine what the test statistic is, it's going to be one of these numbers. It's usually the smaller of the two. Okay. So it might be 13.5. Let's check it out. It says, does the evidence suggest that aspirin affects the median time? So in this case, it says the aspirin effects, and it doesn't say that the aspirin speeds up the clotting process or slows down the clotting process. All right. We think it slows down the clotting process. That's what it's supposed to do. So we'll start off with our null hypothesis. The way it always is starts off. The median of the differences is 0. And then in this case, they didn't commit to being a faster time or a smaller time, but they did say it does affect in some way. And so our null hypothesis or our alternative hypothesis would be the claim. And this would be the median of the differences between the clotting time with and without having taken aspirin. Now, the not equal to is the easiest one, because what you do to determine the test statistic here is to take the minimum of. So for a two-tailed test, you're going to get the minimum of T plus or the absolute value of T minus, which means the minimum between 22.5 and 13.5. And the smallest of those two numbers is 13.5. So our test statistic is 13.5. Anybody have the critical value? Anybody want to commit to a critical value here? I think I've got some. Looks like you're selecting 5 again. Okay, so let me just share a subtle part about this. If alpha is equal to 0.05, then in a two-tailed test, alpha over 2 is half of that. So it's 0.025. And so the alpha that we should choose here, because it's a two-tailed test, we should choose the column of 0.025 because it's a two-tailed test. So instead of selecting this one here, we're going to select this one here. So that's what we've done even in the classical approach. When we had alpha equals 0.05, if we had a two-tailed test, we'd put half of it to the left and half of it to the right so that you get 0.025 to the left and 0.025 to the right. Same idea here. And that's why I wrote alpha or alpha over 2 here. So you come down to your 8, and yes, it's 3. So critical value equals 3. And if you compare the test statistic and the critical value, compare 13.5 to 3, you know that 13.5 is larger than 3, so the test statistic is larger than the critical value, and if that happens, we are going to not reject the null hypothesis. Do not reject the null hypothesis. So, based on our small study here, we don't have enough evidence to say that aspirin has any effect on the clotting time. And you can see here that, we're talking seconds here. Even though there might be some differences here, the time that it takes to clot, however they measure that, in many cases, it's less than a second. In every case, it's a second or less. So I'm not sure that aspirin would even be have a practical significance here. All right, so then we're going to reject the null hypothesis, not fail to reject the null hypothesis. So this is another one where we say there's evidence where there's not enough evidence to support the claim. And you can just say that aspirin plays any role in reducing or lengthening the clotting time. Now, aspirin may have other benefits, but if your goal is to thin out the blood so it doesn't clot as much, it doesn't look like aspirin does it in this case. Okay, so here are 2 problems, and I think we've done problems that would address all of the subtleties, where you get a 0 difference and a two-tailed test versus a one-tailed test, and how you read the table and so on.